Hi, I'm Guy Adams. I'm a Senior Solution Architect at GigaIO. We're here today to demonstrate features of our solution using our memory fabric switch technology that we call FabreX. Our memory switch offers more than just PCI composability due to our ability to route PCIe traffic and use non-transparent bridging, or you'll hear me refer to it as NTB. I'll explain this. Number one, this allows us to offer typical composability, which we'll demonstrate by composing 16 GPUs to a standard 1U dual socket server that has no GPUs in it. And then when we're done, we'll be able to look at it and it'll look as if it was a server with 16 GPUs in it. And then number two, because we route PCIe, we can enable server to server, device to device, device to server communications, all of the angles that you would think of. Our switch fabric now can allow that connectivity to take place. And what that allows us to do is to offer you the ability to build packages like MPI or nickel rings using NVIDIA, or to allow NVMe OF traffic to go across our fabric. And so you can see that, you could have a MPI job that would run across nodes hooked into the same fabrics, and you can use it for your production workload testing, whatever you want. And it's at PCIe speeds and PCIe latencies and DMA access. So a lot of buffering and bounce buffers are avoided. And so before we jump in, I just want to cover a few points of what you're going to see so it doesn't get too confusing. GigaIO offers a command line utility called FM Tool, which you'll see me use a lot, which is our developed tool to allow us to compose devices. It's a simple utility that's installed on a Linux server. That could be a laptop, a rack, a VM, anything that has Linux on it that can talk to the master switch. We also offer a very robust Redfish API, which allows the features of FM Tool, but a lot more. It's a purposely built API to allow our customers to use the open source tools with our FabreX fabric. There's terrific documentation on our portal, and we're happy to share this when appropriate. Next, we have engaged with a few commercial software providers who have integrated our composability into their offering. For example, NVIDIA's Bright Cluster Manager. Supermicro also has some ability to compose with their tools as well. All right, as you'll see during our presentation here, the permutations and combinations of what you can compose they're just simply massive, right? You can do so many things. The reality is that you'll likely have a fixed amount of logical configurations that you desire. But at GigaIO, we don't create those limitations. We just offer you the ability to compose at will. If you'd like to build standard configs, we would probably expect you to do that. All right, now on to our demonstration of composing 16 GPUs to a server and then recomposing 2 servers with 8 GPUs each. For the purpose of the demo, in our lab headquarters, we put together a design that mimics our GigaPod reference architecture. That's what we're going to talk about now. We're going to take a look at the setup. And then following the composing of this, we're going to drop into a nickel ring where we're going to be able to use those GPUs that we've composed at the end. And following that, we're going to have a demonstration of how we run NVMe over Fabric. And those will be using our memory features of our switch, both of those, nickel and NVMe OF. All right. Take a look at our document our picture over here. We have a demo set up on the left. If you can see, it's a description of the hardware that we have to work with. Let's just go down it real quick. We have a couple fabric switches. If I use this hand here, you can see them here and here, and they're named Draco 32 and Draco 15. It's a convention in our lab that we use. Doesn't really matter. The reason I even provide any names is it would be confusing. If you see me issue commands with these names, you might think they're actually flags or something. No, they're the names of the switches, and you can name the switches anything you want. Same way you can name compute nodes and so forth, anything that you want. These are just our names for the sake of the demo so that you don't get confused. All right, we have 3 compute nodes, which are, we named them QCT1, QCT2, and Super Milan 2. We have a storage server that is got 10 NVMe drives to offer out to clients or to initiators, and it's called Super Milan 1. It also has one NVMe for its own boot drive. And we have a couple of accelerator pooling appliances, or what we call APAs. They're these guys right here. And in these guys, there's a drawer on the left half and a drawer on the right half. And when you pull the cover, from the back, you can just slide the drawer out, real easy. And there's 4 slots in each drawer, and you put in the double wide cards that you want. And you can have 4 in a drawer, 2 drawers, that's 8 in an APA. We called them Hydra 12 and Hydra 24, just again, our naming convention. Now over on the right here, this is what we call a topology. What does our composition domain look like when it's all cabled up? And so this shows a pretty exhaustive picture. Let's just walk through it real quick. Here's Draco 15 and Draco 32 switch, like we saw over here. We look real quick, Super Milan 2's in port 1 and 2, port 3 and 4 is empty, Super Milan 1's in 5 and 6. And these are called upstream devices or upstream ports because they're upstream, I guess, is one way to look at it. Downstream are where we have things like our APAs, things that can be composed into upstream. And upstream ports can also be used to connect our switches to downstream ports in our switches, so you can see how we hook them up that way. If you look at Draco 32, we have the server QCT1 we talked about over here in QCT2. We don't have a server in this port 5 and 6, but then we have our APAs over here on the left. Hydra 24 has drawer 1 and drawer 2, and Hydra 12 has drawer 1 and drawer 2, and each of them have identical GPUs in them. So we'll get to that later, but you'll see in a minute when we do it, it'll show you that there's like 40 gig cards in one of these APAs and 80 gig GPUs from NVIDIA, the A100s, in the other one, and that'll allow us a chance to configure it. All right, so let's drop in and actually get going. And let me hit escape here. What's really a good starting point is for us to just actually open the web screen on the switch itself. So all I did was type in http://Draco32. That's our master switch here. And here's what we see. We see that partition 0, which I haven't really described yet, but I will right now. That means on this switch, Draco 32, the first upstream device is partition 0. The next one is partition 1, and partition 2, and so forth. And downstream ports are, you can see over here 7 and 8, 9 and 10, 11, and so forth. As you go across here, you can see that the fastest it could be hooked up was 8-way PCIe lanes. It did negotiate an 8-way. It's an upstream port, and so forth. You can just go down the list and you can see where they're at. If they're down, then they're probably empty, and they're going to continue to wait for us to hot plug in future devices or turn up the links to other switches. The unbound ports are what matter right now to us, because these unbound ports right here that you see, 7, 9, 11, and 13, that means 7 and 8, 9 and 10, 11 and 12, 13 and 14, they're all unbound, which means binding is the term we use to bind them to a server. So like if we want QCT1 to bind to these guys, then we have to actually issue a command, goes in Draco 32 in our software, then takes these devices and binds them to QCT1, which is what we're going to do. Before we jump into that, though, it's very good for us to take a quick peek at these drawers and these devices. And again, the way you do that is you HTTP to that //Hydra HYDRA 24. And then you get login screen, you use the default passwords, and you're in. Now, when you're in, it'll show you that it starts with an overview. Typical screen to go to is the Resource Management tab. And in the Resource Management tab, you get to see that we have 40 gig A100s in this server. And I mean 40 gig, yeah, the 40 gig and 40 gig. And so Hydra 24 has the 40 gig cards in them. You see that you got 8 of them, right? They're all populated. They're all noted here. And in our world, this color matters. So the color now says that this purple color matches that purple color. So this particular retimer that's in this server has the ability to talk to all 4 of these GPUs. It controls them. So when we bind, we will bind this HBA and we will get 4 GPUs. And if we bind this HBA, it's green, it's got these 4. And if we want to do the same thing to double check on Hydra 12, then we would come over here and go http://Hydra 12. And same idea, log back in, it's the other APA, right? And then we'll do the same thing we did the other one. Never say the password. And we go to the resource management and we're going to see 80 gig GPUs in it. And you might ask, well, why didn't you have all the same GPU types? And truth is because in the lab we had a total of 16 GPUs and we had 8 of each type. And so we put those in our demo. You'll see right now they're similarly configured. Before I leave here, the important reason I brought us to this screen is you can simply click on this and say deallocate, and it'll just open this up to be freely used in a different setup. Right now we have 2 retimers in here, so the flexibility is a little less, but we can put 4 retimers in here, and you could hook 1 or 2 of the GPUs, or these slots, so to speak, or GPUs to one retimer, 1 to another, and then we would have more commands to issue, of course, to bind them all, because we'd bind this one and bind this one and bind this one. And you do that by clicking on it, deallocate it, click on them together, allocate them, and it just links them up. As simple as that. So without wasting any more time, let's go ahead and issue some commands here and watch it work. Over here, I have a Linux box that's able to see our management switch Draco 32. So to prove that to you, I can ping Draco 32. There it is. So in Draco 32 is our management switch. He'll be the guy we issue the commands to. We need to bind our GPUs into QCT1. And so what we're going to do is we're going to issue an FM tool command to have that work. And the command that you'll issue with FM tool is, you can see that there's lots of commands. If you do FM tool -H, there's quite a few options, but basically it's a -B for bind. And if you look here in this command, to break it down real quick, and then we won't really have to talk about it anymore, it's binding switch Draco 32. So if you go back to our picture when it's up, you can bind that partition ID 0, and we do port ID 7. That's grabbing the first port 7 and 8, which is that first retimer card that it's cabled to. So now it's going to send that bind command to Draco 32, and we have success. So let's do the same thing for port 9. So this will pick up port 9 and 10 on Draco 32, and that'll grab that other retimer that had the other 4 GPUs. It's going to send that command. And then we're going to do 11, which will pick up 4 more. And then we're going to do 13. So now we can go back and take a look over here at the switch, refresh it here, and we will see that under partition 0, which was QCT1, we've now bound these ports to that partition, and when we reboot, they'll all come back up. So all we have to do now is pop into QCT1, which was partition 0, right here, and we do a reboot. Now, due to the magic of video, we waited a few minutes and QCT1 has been rebooted. And here's our prompt, and to take a look, we can do an lspci command with a tree to lspci-vt and let it expand. And then if we roll back up into our lspci, we should hopefully see 16 GPUs in our configuration, as if they were built right there with it. And look at that, we have 80 gig GPUs and 80 gig GPUs, 8 of them. And then above it, we have 40 gig GPUs and 40 gig for a total of 16 GPUs that are ready to execute right now on this server called QCT1, which was partition 0. If you'd like to see it a different way, sometimes people like to do the SMI command, so you do NVIDIA NVIDIA-SMI-L, and you'll get a different view of them, right? Or you can just do NVIDIA Let's do it that way, just NVIDIA SMI. And it'll give you yet another view. But as you can see, all the GPUs are there. They're able to be used and ready to roll. So we have now accomplished composing 16 GPUs to a single server. And what we need to do now is we need to unbind all of the GPUs and then bind, or we could really just unbind 8, but let's unbind them all. And then we'll bind 8 to 1, which let's do QCT1, and let's bind 8 to another, okay, QCT2. And then take a look, and when we have that done, we'll be ready for us to do a nickel ring with our network transparent bridging abilities that we have. So let's just unbind right now. So I'd put this in my buffer. We'll just paste it in. And so we're going to unbind switch Draco 32 port ID 7 on the master switch Draco 32. And bam, there you go. It's unbound. And we need to unbind all of them, right? So we go back through it again real quick. We got to do 9. It's going to unbind 4 more. And we're going to do 11. And we're going to do 13, right? And then we're going to jump back to that switch, and we're going to see if it agrees that we've now unbound them all. 13. Bang. Okay, it said success on all of them. We come back to our switch over here. Right now, last time we looked at it, they were all hooked up to QCT1. We did an LSPCI and an SMI list. We saw them all there. Now let's just refresh and see what it's done for us now. And it's just unbound them all, just like when we came in the first time. So now we want to bind 4 of those 40 gig A100s on one machine and 4 on the other. And then we want to bind 4 of the 80 gig on one machine and 4 on the other. So let's go back to our server that has FM tool, and we can probably pull back up the command binding right here. Let's go to port 7. So what we're going to do now is we're going to do port 7 to switch to QCT1, which was partition 0. So we can see partition 0 in there, and there's port 7. That just grabbed 4 of the GPUs out of that one drawer. And now if we go to port 11, that'll be one drawer, or one of those retimer cards will be bound, which will grab 4 cards. And that should put the 80 gig, if I remember right, the 80 gig GPUs on partition 0, which is QCT1. And success. Now if we go to QCT2 this time, it's in partition ID 1, and we're going to do number 9. Well, let's take a look real quick over here first. Let's refresh real here, make sure that's what we got. So now we have ports 9 and port 13 because those are already bound to QCT1, see? So now we're going to do 9, right? Let's go back here and double check. 9, yep. And in partition ID 1, bang. And we're going to do 13. Bang. Okay, let's go back to our switch now. We'll hit refresh. And as you can see now, QCT1 has both of those retimers. That's a total of 8 GPUs, as does QCT2. So the same thing we did before, we go to our QCTs. Here's QCT1. We do a reboot. So we can pick up and rescan and get CUDA to load all of the libraries it needs for the access to those. So we'll do a sudo reboot on QCT1. There we go. And we'll do a reboot on QCT2. You can reboot your favorite flavor. I'm just doing it through the Linux system rather than like through a BMC or some other method. But IPMI reboot would work as well. So now we just give it a few minutes for them to reboot. I'll log back in and we will do some LSPCIs and SMI lists and see that we've got 8 GPUs on each of those servers. So now, due to the magic of video, we've waited a few minutes and it's not a big deal, and QCT1 and QCT2 are back up, of which I've got pulled up right in front of me now. You can see QCT1 here, if we do a what is it? Let's try an SM or NVIDIA. Let me click in here first. NVIDIA NVIDIA-SMI command. You can see that there's 8 GPUs. We could also do an LSPCI, put it in tree mode, and we can roll up and see up here that there is going to be a few extra devices we have in this box. Here you go. There's 4 40 gig A100s and 4 80 gig A100s, right? So that's terrific. Let's prove it to ourselves that we did the same thing on QCT2. So we can do LSPCI in tree form, and we can roll up here. And sure enough, there's 40 gig and there's 80 gig. So we have 2 servers that have 8 GPUs apiece, and they're actually in the same order, which makes our next little execution a lot easier, which is going to be how we talk about nickel rings. Again, a nickel ring is a construct built by NVIDIA that allows GPUs on another server to be accessed from GPUs on a, like QCT1's 4 GPUs or 8 could access 4 or 8 GPUs on QCT2. And your code, it appears your code has to be ready for that to happen. And, nickelware. So we were able to build, and it's kind of a long command. We export a path and run it, and I'll show you that in just a second. But it'll run a single loop through. And what I've done over here on these QCTs is I've got a little GPU watcher going. So we can watch on QCT1 and QCT2 as it's executing, watching them use up the GPUs. So we can see that it's working on both of them. Now let's get ready for nickel, and we've already done the composition part. We have hooked, as we just shown, QCT1 has 8 GPUs. The A40s are first, the A80s are next. QCT2 has the identical setup. The A40s are first, and the 40 gigs are first, and the 80 gigs are second. Why that matters is that nickel really strongly recommends and prefers that you use the same type of GPUs in a nickel ring. And for a nickel ring to work, if in NVIDIA land, you would probably be required to go over like an NVLink switch that they're producing, or we don't know yet, but maybe over InfiniBand. But now you can just use our FabreX, and you're at DMA speed, so the bounce buffers are all gone, and you're just talking much faster at the bandwidth of the PCI bus if you're Gen 4, and Gen 5 speeds. So here we go. We're going to give this baby a whirl. So first we CD into the directory I got the test in, which is called nickel tests, and then we run the command. And the command I put in my buffer here, so it's kind of a nasty one. You can see where we export the paths, and all we did was take one of their samples. It's a all reduced perf. We're going to run it, MPI run on host QCT1 and 2, and we're going to use the first 4 GPUs on each of those servers, which will be the 40 gig in our case, just to prove it. Now what we're going to do is, while it's at, we're going to come over here to these QCT servers over here, which have the GPU stat running, and we're going to watch them as it goes. So let's give it a whirl. All right, let's go over here to QCT1. We can see it's beating up those GPUs, right? We can go to QCT2. It's beating up those GPUs. We can kind of toggle back and forth. It runs for about a minute. And we can just watch it. As we know, it's now 100% utilization on these guys and 100% utilization on these guys. Now, if we'd have had 8 and 8 of the exact same type, we would have just changed a few parameters. We could have been using all 16 GPUs across our FabreX. So once again, we've demonstrated that you can have 16 GPUs hooked to one server, or if you really wanted and you had nickel code, you could use our memory fabric and have access to 16 or more GPUs. Which is exciting. Flexibility, you can offer your user community whatever it is that you want, or yourselves if you're doing the science on your own. And you can just see that it just keeps going until, we're going to run up the test in a few minutes, probably a minute here. And watching it go down, I would take a wild guess that we're done, which we are. There's a couple little errors at the end. They're not failures to the fabric. They are just that we haven't had a chance to clean up all of the setup. And I just wanted to be straight about that. So the good news is we've seen the nickel ring perform properly, and we've seen the GPU stat work properly. So the last step, as we take one deep breath, to really demonstrate is how do we do NVMe over Fabric, right? NVMe over Fabric is not limited to just using our FabreX switch, right? You can do it over InfiniBand or other ones, but our FabreX switch offers some advantages because there again is DMA access, right? The NTB, the transparent bridging, provides you access without having to go through all the bounce buffers, a buffer to hold the data when it comes in. Even if it doesn't go to the CPU, it just has to buffer the data going across NICs, whether they're going across an InfiniBand or whether they're going across Ethernet. Well, here, they're just feeling like they're talking natively to each other over DMA. So NVMe over Fabric works the same way. We go to a server, in our case it's called Super Milan 1, which was, as we talked about early on, the server that has 10 of the NVMe drives in it. But I kind of want to talk for a second about the difference between how we offer access to NVMe drives. We offer two types of local storage, composability, if you will. One's composing truly, and the other's using our memory fabric, which is NVMe over Fabric. And so, one, true composability with our storage pooling appliance. It looks very much like our accelerator pooling appliance, but it has NVMe slots in it that you can literally do the same thing with FM tool we did there, and you can hook drives or multiple drives or series of drives, whatever it is that you want, into a server, and it looks as if it's locally installed, the same way the GPUs look like they're locally just sitting right inside that box. And that's great, but the granularity of that's a little limited. Let's say you had some 15 terabyte expensive NVMe drives in there, but your users only needed a couple of terabytes of scratch space locally. Well, you can't just go say, give me 2 terabytes. You have to, it's by device. So it would give you the minimum of 1 drive size. The alternative that we like and we recommend, although we give you the choice yourself, is that we say, well, if you buy a server with those NVMe drives in it, like we did here, then you can use the NVMe over Fabric, and I'll show you how that works. And you can then, per the NVMe over Fabric, which is often called NVMe OF, it has its own rules on how you set up the export file, so to speak, if you're an old NFSer like me. And you can set up parts of disks, multiple disks. You can do all sorts of things, whatever the rules are defined. And an O'Reilly book will give you a lot more detail than me. I am not a guru at this, but I understand enough now not to be scared of it. I used to be scared of it, and it's really nothing to be scared of. And so I wanted to share with you guys sort of the concept of how NVMe over Fabric works. If you don't know, and if you do know, you're smarter than I am at it already. Bottom line is you have a server, and they call it a target. And in our case, it's called Super Milan 1, and that has the drives. And then you have clients, which they call initiators, which then access those NVMe drives or parts of the drives or whatever it is that you've exported. And you do that exporting instead of like a export file, config type file, you do it in a JSON file per the rules. And I'll show you what we set up because we did it very simplistically. But as you can imagine, anything that you can export through NVMe OF, you can share amongst any of the other initiators. And the way we look at that is we look inside the JSON file, which is, well, first of all, let's start out with the real basics. Let's do an ls block. And you can see that there are actually 11 NVMe drives. There's this NVMe here 1, and then there's 10 others below it. That's because this is the boot drive, and we don't want to mess with the boot drive. So there's 10 additional NVMe drives in here, and they're all 1.8 terabyte in size in our case, although most commonly we would expect to see larger ones, probably 15. This is just, again, for our demo. And we're going to export these drives, and just for fun, we decided we should try, let's export 10 of them. And then let's just go ahead and make a target, and let's grab all 10 just to show we can get some number of them without any problem. So that's the demo today, is to take these 10 drives, export them here on the target, and from the initiator, I think I'll probably pick on QCT1, we'll just grab them, and it'll look as if they're just mounted right there as a dev device, and you can build a file system on them. We have a little FIO program we'll run to show that we can access them without a problem, and you'll just get the chance to see it. Okay, so let's look at the config file, or actually they call it the JSON file. So we do, let's see if it's here. There's a JSON file here called 10x JSON, target.jpos. So we cat it, or let's vi it, so it's easier, vi, target JSON. There we go. So if we go kind of to the top, and again, if you grab an O'Reilly book or you do some education on it, you'll be smarter than us fast. But the bottom line is you define who you are, information about yourself. I'm, Super Milan 1. Here's who I am. And then I'm going to go down below it and I'm going to define some information about me. Most importantly, I'm going to make the name of my drives or my VLANs, and I'm going to have some naming convention that I make up. And then I'm going to go define that down below. So again, as you spend a little time just looking through the manual, this is kind of the bread and butter of the target, right? You go in, you build this JSON file, and then you basically export it. And we'll do that together. And then all of these will be exported for any initiator that's on our FabreX fabric to be able to have access to. And we'll do that on QCT1. So let's just roll down for a second and show you a couple things. First of all, you can see here it allows any host. You can define it. You can say I only want certain hosts to have certain VLANs and so forth. We didn't want to limit it. If anybody in the fabric wanted to have it, they could mount it. We got very specific by pointing specifically to an NVMe drive by name, and that was a little bit of an education curve on our part. We had there's other ways to do it, and this always guaranteed that when we mounted node 1, it always got for sure this drive. And in our case, if you look at how we did it, and I don't know the exact stanza, but we basically just chose one drive per VLAN. And again, it's just for our simplicity of the demo. I'm not really going to spend a lot more time because this is all in O'Reilly books, but to give you an idea overall, you basically are building an export file, and we're going to export it. So let's get out of this. Well, now that we've looked at the contents of the JSON file, what we ought to do is look to see what's exported. So there's a command called sudo NVMe TCLI ls, and that shows us that right now there's nothing exported, no hosts, no ports, no subsystems, anything. So what we want to do is export those drives, and the way we do that is with a restore command, and it is let me put it into my buffer over here to restore it, and we will go for it. It's a sudo NVMe TCLI of that JSON file. So here it comes out of the buffer, paste, and okay. Now it ran the command because I caught a carriage return, but let's rerun that sudo ls and see what we have now. And lo and behold, look at that. We have all of these drives are exported from the target such that initiators can pick them up. So that'll be what we do now. We're done with our target, which is Super Milan 1. We've got the drives and everything defined we want. We've exported them out so people can, have access to them. And now we're going to go to, QCT1, and we're going to, mount them, so to speak. All right. So now that we're there, we will take a look. Well, first of all, let's do a LSBLK, right? Let's take a look. Here we go, just to show everybody, there's only one NVMe drive in this here, and it's right down here. And that's our boot drive that's on this local server called QCT1. And now what we want to do is mount 10 more drives just because we can. And we haven't written a little script to do this. And so we want to look at this script called connect 10x. So let's just cat it, connect 10x subsystem sh. And the reason I wanted to do this with you guys is to show you I could type in some fairly long commands, but I suspect just about everybody that does NVMe over Fabric eventually puts a script like this, or certainly saves it once they do it once, because you have to issue an NVMe connect with the transport of non-transparent bridging, your queues, your delays, your control times, and then it needs to append for each one of the nodes some other specific data like, what is the, device is talking through, and other stuff like that. So we have some other CLI, we've tried different block sizes and things, just we were experimenting, but right now we're going to mount them with a 256 queue size. And you can see down here, we call that subroutine 10 times each for 10 of the nodes. So let's just run that. I mean, that's, let's mount them up. So let's do /connect 10 system subshell, and we'll watch what it does. The last thing it does if you see right here, the last thing it does is a list command that will show us what is mounted. We can do it again, which, in fact, let's do it again just for fun. Here it is. Oops, let's just cut and paste this, bang. Okay, we'll do it one more time. This time I'll do it the right way. My goodness. Okay, there it is. And so what we can see down here, I know it's a little busy, but the node and the drives. And as you can see now, we have the boot drive in that position, like we saw before when we do an LS block. Now we have 1, 2, 3. The reason I like this list is this tells us that this is on a Micron and it's local to the machine because you know all the stats of it. And then all of these tell you that they're mounted from Linux since they're NVMe OF drives. So these 10 drives now came from our target, which is Supermicro 1. Pretty cool. So now we have the 10 drives locally mounted here, and just to prove we can access them, I mean, you could build a file system on them, format them, you do whatever you want, but we have a little FIO program that we wrote that will just do a little bit of quick IO. So we have to CD to, we'll come back over here, and there we go, CD to FIO, and then there's a program that it's .run _ quick file _ new ACE 2, and the only reason that these are specific to this is we trimmed up a test script that we have that does like 30 minutes worth of FIO work and just made it so it'll run in like a minute or so. So this script here is running an FIO. In fact, we can cat that out after. Well, let's cat it out now. Cat runs quick info quick file _ new ACE 2.sh. And so I could have VI'd it, I guess, might have been smarter, but at the very bottom line, at the very top, all we did was shorten up our little script here to run a simple test of looping through it, I don't know, about 10 times on read. So let's do that. Let's just run this right now. So again, it's run quick IO _ new ACE 2.sh, and off we go. We stopped this at the very beginning with the tag just to, we can control when it executes. So here we go. Now it's going to run for about a minute while we sit here and watch, and it's kind of neat, but I can finish chatting a little bit. It's not so important that we're running the FIO. What's important is that we have now used our memory fabric, not composition in this case, to provide those 10 NVMe. And we could have provided 1, we could have provided 2, 4, 6, whatever we want. We could have, in the target Super Milan, we could have divided those, NVMe drives up into smaller increments, other combinations. And we could have, definitely, mounted those, so to speak, as well. So what this shows you is that you get the, absolute best flexibility, and by having the ability to route the PCIe traffic, we can set up the fabric to give us that access, and it's really exciting. So it's great to have that. And as I told you before, the alternative that we could have done, which I don't have a device hooked to this setup, but we do have the ability for you to compose, and that would have been a different alternative. But remember, when you compose at the device level, so you would have to compose at least one full device per each one of these. Even though in our case we did compose a device, that's that flexibility is gone for you with composition. So again, the beautiful part about our solution is you get choices. All right, here we go. FIOs come back. We could go up higher. I don't know how to read all the FIO outputs very well. And if y'all do, that's great. But what I do know is to come down here at the bottom and look how fast it ran. To, like, bandwidth was 12.2 gigabytes a second, and the other parameters. And that's pretty great. It's getting real close to, right up there in the maximum speed you can run. So we're excited about having options to offer you guys, and we just hope that this demo has been illuminating on the various options that we have. Again, what did we do? We did composition, and we did memory fabric work. We did composition with the GPUs, hooking them up to our servers, and running a nickel ring was using our memory fabric, and now running NVMe over fabric using our memory fabric. So have a great day. Thanks.